times the time for how long you're traveling at that speed. And we'll do three basic problem types. So if I have opposite direction, that means I have two objects traveling in the opposite direction. So they could start at the same point. One could travel east, one could travel west. Or they could be at opposite ends traveling toward each other. And the way you would set this information up in an equation, the rate time of one object plus the rate time of the other object equals the total distance covered by both objects together. Two objects traveling in the same direction. That means I have one object leaving and traveling, and then at a later time, a second object leaves traveling faster in an effort to catch up with the first object. So they're both traveling the same distance, so the rate time of the first object would be set equal to the rate time of the second object. And then the round trip. You're at home and you leave going to a destination. You reach your destination and you turn around and you come back home taking the exact same route. So you've traveled the same distance on both legs of your trip. So the rate time going is congruent or equal to the rate time coming home. So what's in red, those are the equation setups that you'll use once you organize all of the information in a problem. Okay, let's do an opposite direction problem. Two planes leave Atlanta at the same time, one flying at a speed 20 kilometers greater than the other, and the jet is flying west. After 4 hours, they're 6,000 kilometers apart. So I have to understand what's going on. One plane flying east, the other jet flying west. We're told that they're 6,000 kilometers apart after 4 hours. So I have my chart. We can do east and west, eastbound, westbound. And your variable in the problem will either be the R, the rate, or the time. In this particular problem, we're told that they're both traveling for 4 hours. So time column can be 4. And the rate of the plane flying east is 20 kilometers greater than the jet flying west. So if I let R represent the rate of the westbound plane, then R plus 20 greater would be the rate for the eastbound plane. And then the distance column is simply the rate times the time. And then you look at the initial setup that I provided above. Two objects traveling in the opposite direction. The rate time of one plus the rate time of the other equals the total distance covered by both planes. In this particular problem, that is 6,000. Then you slip in your algebra from your last column, slip in your expressions to represent what's going on, and then simply solve this for R. So the rate of the westbound plane is 740 kilometers per hour. The rate of the eastbound plane would be 760 kilometers per hour. Okay, two objects traveling in the same direction. A small plane leaves the airport and flies north, traveling at 240 miles per hour. A larger plane leaving 30 minutes later, following the same flight plan, flying at a rate of 360 miles per hour. How long will it take the larger plane to overtake the smaller plane? So for labeling, you could have small plane, large plane. The rate is straight out given. Rate of each is given information. If I let t be the travel time for the small plane, since the larger plane leaves 30 minutes later, its time in the air would be the small plane's time minus 1/2. Notice that the rates are given in miles per hour, so I would take the fractional portion of an hour that represents 30 minutes, 1/2 or 0.5, so that you stay in miles per hour. And then finally, your last column is distance. So simply multiply the rate times the time, the expression to represent that. And then the initial setup that represents what's going on. The rate time of one is equivalent to the rate time of the other. So you take your last box, your distance box, and you set the two expressions equal to each other. So here I would have 240t getting set equal to 360 t minus 1/2 times t minus 1/2. And solving that for t, you can, I'll let you all get through that. T ends up being the fraction 180 over 120. This represents time. So I need to take this and turn this into time. And if I do the mixed number, that's actually 1.5. So that represents 1.5 hours. 1.5 hours. And then you have to go back to your chart. When you look at your chart, you see that you let that 1.5 hours, that represents the flying time for the small plane. So if the large plane is in the air the same amount of time as the small plane minus 1/2, 1.5 hours minus 1/2 gives you 1 hour. So it would take the larger plane 1 hour to catch up with the smaller plane. So when your variable is t, you have to then interpret that final answer into something that makes sense in the real world. And then a round trip. Sam hiked up a hill at 4 kilometers per hour and back down at 6. His total hiking time was 3 hours. How long did it take him to hike up and how long to hike back down? So this is my round trip. So both, assuming he takes the same path, set equal to each other. Rate time up equals rate time down, assuming he took exactly the same path. So I've got up and I've got down. His rate going up was 4, his rate coming down was 6. His total hiking time was 3 hours. So up and back, a total of 3 hours. If I let up be represented by the variable t for time, then 3 hours minus t would represent how long it would take him to climb back down the mountain. And then filling in your last column, taking the two expressions, setting them equal to each other, solving this for t, and I need to interpret that into something that makes sense in the real world. The mixed number would be 1 8/10. And I can think about what portion of an hour 8/10 is. If I multiply 10 times 6, I get to 60 minutes. So this gives me 1 hour and 48 minutes. So 1 hour and 48 minutes. That represents his time up. And when I subtract that from 3 hours, his time coming down would be 1 hour and 12 minutes. 1 hour and 12 minutes down. So just make sure that when the variable is t, you interpret it into something that makes sense in the real world.